and I'm going to present a minimal TTE framework for verifiable confidential microservice deployment. So I want to start by talking about confidential computing. So if you guys don't know what confidential computing is, basically it's the ability to protect data use. Usually it's done via TTEs, where you would have one-time encryption, isolation of a given workload from other workloads. You have attestation, which is verifiability, the ability to trust your workload. And you have functionality in terms of sealing persistent data once they're outside of the CPU. So confidential computing has gained a lot of traction recently with the rise of generative AI, because confidential computing mainly uses hardware, and with those special trust characteristics, especially with agentic systems and the amount of data that are going to the cloud from inferencing, from people just sharing a lot of data with large language models and LLMs, confidential computing, because it uses hardware to trust software, it has special characteristics that allows it to protect AI systems in the cloud better than other solutions. So what does it protect, and what is the threat model, and who does it protect? So in our research, we basically scoped it down to a platform engineer that wants to deploy a large language model to the cloud. Basically, usually in organization, they would use Kubernetes as their main computing fabric, and they would deploy containers on top of it. And the platform engineer would either want to protect the weights and biases for their AI models, or they want to give users the trust and the privacy guarantees that their data that's being processed in the cloud is confidential and trustworthy, or no one else are able to see them. So confidential computing provides two pillars, which are confidentiality and integrity. So confidentiality is usually guaranteed by trusted execution environments, TTEs, which is basically the ability to put software inside of an encrypted enclave where it's isolated from the external world, and trust via TPMs and an overlying software called the integrity measurement architecture that continuously verifies the integrity of your software. However, when we were doing the research, we were trying to see, all right, how can we use confidential computing to actually provide this end-to-end confidentiality and integrity for AI workloads in the cloud? And most of the work, either in the quadrant of trust only, where you have TPMs and integrity measurement architecture, they do a good job at verifying your workload in the cloud, or they do a good job at confidentiality. But the ability to actually deploy your workload end to end and have end to end integrity and confidentiality for your trusted workload to establish privacy is something that was really seen in the literature. So we tried to actually fix it. We tried to implement a protocol that allows you to have end-to-end confidentiality and integrity. And we faced three main issues, and that's what we solved in C. So the first issue is the TTE dilemma, which is if you have a small TTE, you are limited with the functionality. You delegate functionality outside of the enclave, and that basically weakens security because you're trusting something outside of the trusted domain. And if you have a big TTE, you are basically putting a lot of functionality inside of the TCV and expanding your attack surface. However, during my research, I came across a very seminal paper that argues that modern operating systems are not suitable for cloud because modern operating systems are general purpose and they are made for system admins, for people to use their graph UI and stuff like that. While the cloud abstracts a lot of those functionality when you actually want to deploy workload to the cloud, and those get deprioritized in favor of container workflows, security, scalability, and fast performance. So we took it a step further, saying that it's not just not suitable for the cloud, it's also not suitable for trusted execution environment because TTEs also further abstract what you can do with an operating system. So a lot of stuff, a lot of features that the operating system provides are redundant and already provided by the TPE itself. So with that, we were able to basically study the Linux kernel, the different operating systems that can run inside a TPE, which includes library OS, unikernel, and other monitors. But each one had a specific weakness that disallowed this end-to-end integrity and confidentiality verification. So based on that, we took a UKL, which is a unikernel for Linux developed by Red Hat, and we tried to make it fit our end-to-end protocol. And I'll talk about more about the TCP that we implemented. But we, the things that get prioritized based on issue one are actually container workloads. So when you want to deploy something to the cloud, you want to make it automatic, you want to streamline it. And the way that it's usually done is either in the cloud via containers like container runtimes or like Kubernetes and stuff like that. And if you want to have this end-to-end deployment, you need to have your operating system working with containers. So that's the second issue. And trust is the third issue, is that if you want to have this end-to-end confidentiality, you need to actually deploy the container after the TTE is actually running, because you need to maintain this end-to-end confidentiality. So how can you maintain trust if TCPs usually have a mutable TCP, meaning that if you have a TCP, it doesn't change anymore. So this is the architecture that we basically made, where we have a configuration and attestation service that runs inside our TPE, and you have a user that is like literally a CLI, and basically the user would encrypt on his end the container, would sign it, and then it would go to an encrypted container registry, and then it would be deployed at runtime in our TCP. So the reason that we were able to do that is with the TCP's design, instead of statically linking the container inside TCP at compile time, we statically link the container runtime directly inside the Linux kernel, abstracting a lot of user space functionality. So with this approach, we created our own container runtime, and we stripped a lot of capabilities and optimized it for container workflows and security. So we formalized it in a push, run, prove workflow, and this is basically how we enabled continuous trust, because our framework broke the immutable TCP architecture. So since our TCP optimization allowed us to export containers as a first-class citizens of the Linux kernel, we were able to have granular verification at the container level that allows us to do integrity measurement architecture, achieving our end-to-end deployment protocol. So yes, basically this is seed. We minimized the TCP and we allowed OCI, unmodified containers, to run end-to-end. And we were able to prove that our end-to-end protocol actually works against most of the attacks that are defined in the literature. Thank you.